We're almost done with chapter 2. We're going to do 2.7 and 2.8, but they're kind of like the same thing. It's called fitting a model to data, where we look at some tables and some points and try to figure out what kind of variation equation we have. The question for the day is, how can you determine what variation equation to use given a certain table? So in class, we actually read through like this little thing here, and you can read that if you'd like. But it's basically just talking about um, somebody was dropping different various objects at different heights, and they were trying to see what would fall faster. And in general, it turns out that almost everything will, as long as you don't have wind resistance, assuming no resistance on the objects, that it should fall at the same rate and hit the ground at the same time. So our first example kind of leads into that. It's talking about dropping a ball. It says the table below gives the distance d in meters that a ball travels in t seconds after it is dropped from the top of a cliff. The order of pairs in the table are listed below. So you look down here, we have how long it is in the air, time in seconds, 1, 1.5, 2, 2.53. And the same thing is the distance, measuring the distance in meters. It goes from 4.9 up to 44.1 meters. So we're going to practice using this in Desmos. I'll show you how to do that. We're going to put this table in. So using Desmos, if you hit the plus sign here, you'll see where it says table. Click table, and we're just going to copy down those numbers here. So I'm just going to type them in. So we have 1. You can hit enter, or you can hit the arrow down on your keyboard. And then I'll do the same thing with these numbers. I'm actually going to move it over so I can see them at the same time. There we go. And as you can see, you can only see one dot here, just the 1 4.9. So if I go back to our notes here, we're going to actually change the scales so that way we can kind of see this a little better. So what I'm going to do is I just chose some numbers outside of our x values here. So this goes from 1 to 3. I went from -1 to 9. And on the y values, I started at -20 and went up to 150. But you could kind of do whatever you wanted to do in that sense, as long as you can see all the points. So I'll try to do that as well. You're going to click on this little wrench here. It says graph settings. And then we're going to change these numbers. So we have -1 to 9. Then down here, I think I put -20 to, what was it? 150. There, now you can kind of see the general shape. Moving on to part B, it says which variation equation should be used for this data set? So the question is, what kind of graph does it look like? So I'll give you some examples. If you remember that y equals kx is the same thing as lines that kind of go like this. They're straight. Y equals kx squared are like the parabola ones, look like this. Not the best drawing. Y equals k over x, they're like these ones that have these two separate branches in opposite quadrants. And then y equals k over x squared looks like it has a branch on the top, kind of like the previous one, but this has a branch on the top and it has a branch next to it. So the question is, where do these points lie? Well, we're looking only at the first quadrant, so we're only looking at, bring this over here. We're only looking at this quadrant to see what the points look like in that quadrant. So which one does it match up with? I think what we have going here is it kind of looks like it's a straight line, but it actually looks like it's kind of curving near the end. So maybe it's kind of like more of a curve. I think it probably is going to be this y equals kx squared, where we're seeing like half of the parabola. So we'll go with that one. We're going to create a variation equation using this equation here, but we're going to change out the letters to d and t rather than using y and x. So I'm going to change y into d equals, k will stay there, t will be changed from x, t squared. Part D, substitute one of the ordered pairs from the table into your equation to find k. So now that we know what it is, we can use any ordered pair we want to find the k value. So I'll go ahead and just use the first one. It seems like it's the easiest. Our time is 1, and our distance is 4.9. So I'll put in time 1 and distance 4.9. So we do 4.9 equals k times 1 squared. 1 squared is just 1. So k times 1 equals 4.9. Well, you could divide both sides by 1 or just realize that this is the same thing as saying k equals 4.9. And that's our k value. Pretty simple to solve. Part E says rewrite your new variation equation using k. So we're going to have our new equation, but we're putting k with it. So this should be d equals 4.9 t squared. So we're going to type this into Desmos to see if it actually works. I'm going to type in this equation using y and x. In the second line, you can type in y equals 4.9 x, and then make sure you hold Shift 6 to get this squared. And as you can see, it actually hits all the points. And it's like this really wide parabola. So we know that it works. So we check that off. Good. Last part of this question says, predict the distance the ball travels after 6 seconds using this variation equation. Then we'll check it in Desmos. So after 6 seconds, that means that's going to be our time. We're going to plug that in for t. We're going to find how far the ball has traveled. So we have d equals 4.9. And then we're going to plug in 6. So we have to do 6 squared and then times it by 4.9. So 4.9, 6 squared is 36, and then just multiply that together. So I'm just going to put in the calculator, and I got 176.4. This is in meters. So after 6 seconds, we hit 176.4 meters. Again, I'm going to check this in Desmos. I'm going to see if this point 6 comma 176.4 actually is on our new parabola that we just made. So I'm going to make a new line. Oh, no, you can go up here. I'll go up here. And we're going to put in 6 seconds. And then we're going to type in 176.4. And just to see if it's on there. Go over here and check. Oh, 6 over here. So I'm going to go over to 6. Here's 6. Go up on the graph and see if it's up there. And there it is. It's right on the graph. So it works. All right, we'll try another one. Find the variation equation, describe this data set. So I'm going to go through the same kind of steps, and I'm going to change the scale probably. So I'm going to move this over so I can type in the equation, the table. So again, you hit plus table. Then we're going to go ahead and fill that in. So we have 2, 3, 4, 5, 6. And then I'm going to go over here and change those numbers. So we have 12.8. Then we have 28.8, 51.2, 80, 115.2. Again, every time we plot these, we're going to have to probably adjust this. I'm going to zoom out a little bit so you can see it. If you need to adjust this at all, you can always go in here and I usually just pick values that are around this number. So I could probably go from like 0 to 10 on the X. And on this side, I would probably start at like maybe 0 again, and maybe go up to like 120, 130. So if you can't see it right, you can always change that. And the question is, what kind of shape is this? Well, it looks kind of a lot like the one that we just did, which was y equals kx squared. So I'm going to go ahead and use that one this time, just like we did last time. So what variation equation would you want to use? We'll use y equals kx squared. And just like before, we're going to take one of the ordered pairs to make sure that we're good. I'm going to use 5 and 80. So we're going to do 80 equals k times 5 squared. So that would be k times 25 equals 80. Divide by 25. Let's see what you get. I got 3.2. So rewrite your new variation equation using k. So we have y equals 3.2x squared. Type into Desmos and check it. So let's do that. Keep that open. New equation, y equals 3.2x to the second power. And there it is. If you want to change the color of this, you can. That is it in this setting? Yeah. If you hit the gear icon, you can change the color if you'd like. I'll change it to orange. How about that? And it goes through all the points. Last problem. Predict the value of y when x is equal to negative 5.5. So now that we know our k value, we'll plug in negative 5.5. So we have 3.2 times negative 5.5 squared. Don't forget, when you square a negative, it turns into a positive. So 5.5 squared is 30.25. So we have 3.2 times 30.25. And then we're going to get, I got 96.8. So we'll go ahead and check and see if this works. So do we have the point negative 5.5, whoops, comma, 96.8. So all I have to do is type in the x value and the y value to see if it's going to work. So we'll put it over here. So negative 5.5 and 96.8. And hopefully you can see on my screen that it is hitting this parabola on the line. So our prediction was right. We only have one more example, I do believe, and then you have two to try yourself. The next one is a little bit more difficult because it's about kind of like collecting data. So like we may not be able to hit every single point on the line when we do this. And it's also confusing because it could be a possibility of more than one thing when we do it. So let's go through it. So Anna and her sister Jenna went to the playground to play on a seesaw. As an experiment, they had Anna sit at a fixed point on one side of the seesaw, while 9 of her friends took turns sitting on the other side and tried balancing the seesaw. When the seesaw did balance, Jenna measured each person's distance, d, from the pivot, and then recorded their weight, w. The results are shown in the table. So we have to make another table. We're going to use Desmos to do that, and then we're going to pick a good scale for both x and y. So let's first fill in the scale before I put it in the table. So I'm going to change the scale to, we're going from 70 pounds, which is the lightest, I think, all the way up to 206. So let's maybe do it from like 50 pounds to 220. I'm just picking, values on each side of this number. Oh yeah, we should probably label this as X and then D. Here we go. No, not D. X and then Y. The Y value, we're going to go from the lowest it goes down to is 0.6. So maybe I'll start at 0. And then the highest it goes up to is 1.7. So maybe I'll go up to like 3. So let's go ahead and plot the points. So delete these. Okay. 70, 80, 85, 100, 109, 133, 170, 206. Okay, so let's go ahead and change our scales since I can't really see any of the values. And what we say was 50 to 220 on X. Y values were 0. And if you don't like these values, you can also change them to 3. So once you have them all in there, then you can zoom in and zoom out to kind of look at it a little bit better. But at least now we can see everything. It's easier to zoom in and zoom out. So now we kind of got like this curve coming down here. So what did that look like? If we go back to the problems, if you remember the graphs, like back here, we're still in the first quadrant. So I'm thinking it's not going to be this one that goes straight up. It's not going to be our parabola. It looks like we have these two options, which unfortunately they kind of look the same. So we don't know which one it's going to be, but we're pretty sure it's going to be one of these two. So let's go back to our question here. It says, what variation equation could be used for this table? So we could actually use one of two things. We could do the k over x, or it could be y equals k over x squared. So we're going to test a point to find k for both possible equations. So let's pick a nice point, nothing too terrible. Maybe we'll try this one, 71.7. So x is 70 and 1.7 is y. So we have 1.7 equals k over 70, or 1.7 equals k over 70 squared. So we'll actually figure out what both of these are and then see which one makes more sense when we put it into Desmos. So we'll multiply both sides here by 70, so 1.7 times 70. I get 119 equals k. Over here, I had to do 70 squared first, which is actually 4,900. So I get 1.7 equals k over 4,900. Multiply both sides by 4,900. Times 1.7. I got 8,330 equals k. So remember, in the left-hand side, we would have the equation y equals 119 over x. And the right-hand side, we'd have y equals 8,330 over x squared. So we're going to test both of these just to see which one would work better. So we have y equals 119 over x. Well, I don't even know if I even checked the other one. Look at all these points that are going through. And the other one we had was y equals 8,330, 8,330, divided by x squared. So this one actually only goes through the one point that we looked at, and we don't have that at all. So this one is actually much more steep than the other one. So we don't need the second one. The first one was correct. So we're going to just take this one out and say, hey, it's y equals 119 over x. And we're going to use that in our last problem. 119 over x. How far away would Anna's friend Curtis have to sit if he weighed 190 pounds? Check the point using Desmos. Okay, so we're going to put 190 in for our weight. I guess I should have been using d and y for distance. But this goes in for our x value. So we're going to have 119 divided by 190. Let's see what we get. I got 0.626. I'm just going to stop there. And we're going to test our new point, 190, 0.626, to see how accurate that is. The next number was 3, so I didn't round up or down from there. I just kept it the same. So let's try that. 190. 190. And then 0.626. I don't know if you noticed it could pop up, but it's right there. And it's on our line. The rest of the problems are for you to try. There's only 2 huddle problems to try. And again, you want to see if you can figure out which equation it falls under, depending on what quadrants it falls under. Otherwise, that is it for section 2.7. And then the next day will be 2.8, where we're going to be doing this a little bit more, and we're going to add in the combined and probably just combined variation as well.